Oh, hey there. I almost forgot you were there. It's been a little while, hasn't it? Well, better late than never, right? What I have here is finally starting to look like a proper CubeSat. I have three layers. The EPS layer on the bottom, which provides power to the system, the avionics board in the middle, which is command and control and has sensors, and the most important board for the CubeSat, the radio board. Without it, you can't talk to the CubeSat and, well, there's not really much point. The radio is based on the OpenLST design, so I had pretty good confidence that it would work, but it was my first time laying out an RF circuit, and I had to swap out a whole bunch of the components. I was pretty happy when it actually turned out, and yeah, I can communicate with this other radio board, which is a clone of this one. The radio is pretty much a clone of the OpenLST design, except I had to swap out a whole bunch of the parts for available alternatives. I also removed the onboard 3.6 volt LDO, which converted 5 volts to 3.6 volts to power the RF front end. Instead, I connect the RF front end's high power input directly to the lithium-ion battery on board, which saves on complexity, and it seems like the RF front end was designed this way, where it accepts 4.2 volts to 2.5 volts for its high power input. The radio is configured to transmit and receive at 437 megahertz. I actually did not change the default configuration OpenLST provided. I wanted to make sure that the defaults actually worked before I started messing around with what are very register-specific settings in order to change the frequency. And this isn't ideal, as the balun that I use is only specified for 430 to 435 megahertz. But looking at the provided charts with the balun's datasheet, it actually looks like 437 megahertz is pretty much going to behave exactly the same as 430 or 435 megahertz. Being off by a couple megahertz really isn't a big deal. That's true for the rest of the RF front end as well, where it'll work from between 430 to 440 megahertz without any issues. Let's talk about the software for the radio. As I said earlier, I wanted to keep my changes minimal. I write software for a living, and I don't want to spend too much of my free time writing even more software. To make this a functional CubeSat, it needs to be able to report its state of health, which includes things like battery voltages, any sensors, and things like that. But first, the CubeSat needs to power on the radio. Simply turned on, the radio consumes approximately 150 milliamps at 3.3 volts, so it can't be on all the time. The avionics computer must regulate when the radio is on and off. Let's go through the entire process from power on to transmit. So there's a couple layers of software going on here. There's the EPS, the avionics board, the radio, and then whatever other radio the CubeSat is talking to. Right. So the avionics board, which is again the board in the middle, it requests that the EPS board, which controls all the power, turn on the 3.3 volt rail, turn on the battery. Then the avionics board talks to the radio, makes sure that the radio is alive, and then what it does is it sends the state of health to the radio, and the radio caches that. The radio then waits for any incoming request. Once it sees an incoming request for the state of health, it will then respond with the cached state of health. I did it this way such that this radio does not just continually transmit and burn a whole bunch of power, and that way I can kind of control just when it is actively transmitting, since presumably I would control when I am using this radio, which is connected to my computer. So if I transmit from this guy, only then will the CubeSat respond. In practice, I could change this such that the CubeSat is more talkative, but that's just a configuration. It is important to note some limitations with the CC1110, specifically the F32 variant of the radio transceiver, which is the heart of this radio board. Specifically, as it comes to the amount of RAM that it has. The F32 variant has 32 kilobytes of program flash and only 4 kilobytes of RAM. If you use the F16 or the F8 variant of the CC1110, you get correspondingly 2 kilobytes of RAM or 1 kilobyte of RAM. It's important that you get the F32 variant because the OpenLST program, before I made any modifications to it, only had 150 bytes of free RAM. There's probably some stuff I can do to cut that down, but it's a pretty slim margin. As compared to the program flash, it has 32 kilobytes of program flash, and it only uses about 5 kilobytes of that, so there's plenty of room there for a larger program. RAM is really just the concern. The limitation is manageable in software. It's easy to work within the 4 kilobyte boundary, even though it is a bit of a pain, but it is difficult to get the F32 version of this chip. In fact, the chip that you see right here, this is a knockoff I got from eBay, which claims to be the authentic article, but it probably isn't, or maybe it is, I have no idea. Either way, it works fine, so, you know, that's nice. DigiKey and Mouser both had really long lead times for this item, and I haven't checked again to see if the lead times have gone down. Maybe it's just some supply chain thing that was happening 6 to 8 months ago. Alright, well I did say that this radio works, and I haven't actually showed you that. So let me get these two set up and get some blinking lights going, and I'll show you what the terminal output on my computer looks like. So I'm outputting to the test RF connection that I have instead of going through the RF front end. The RF front end works, I have tested it, but just to avoid putting too much power out through the RF, I just go through the test output. So there's no amplification happening. I also have 30 dB attenuators on each antenna just to be safe as well. And then I can connect the batteries. This board comes to life. There's power on the radio. There's power on this radio. And so this radio just has 3.3 volts. I don't need high power since I'm not using the front end. This guy is hooked up. Even though it has battery power, it's just hooked up to use, not hooked up to use the high power amplifier. And if you can see on the power supply here, 3.3 volts at just about 150 milliamps, that's hooked up to this radio. All right, so I brought my computer into frame here. So there's a terminal application that runs all of the OpenLST communication. There's a UART binary protocol that talks to this radio. So all those details are on the OpenLST repository that I have forked. I've converted most of the scripts to run Python 3 instead of Python 2, which made things a little bit easier since I had to add in some Google Protobuf support in order to decode packets that I send from the CubeSat. So I'm sending commands to this radio with the destination ID of 4, and this radio has its ID set to 4. So I send the get external command, and after just a little while, it comes back with some battery voltage information, some solar voltage information, and some information on what each power rail is set to. And if we run it again, we get similar but slightly different results. And just to prove that this is actually communicating with this guy, we can turn off power and run the command again, and we'll see that nothing happens. Alright, so I've turned off this radio, and I did that by just disconnecting one of the battery supplies, and the avionics board knows that if one of the batteries is gone, it should turn off the radio, so the radio is off. Rerunning the command will just continually hang as there is nothing to get a signal back from. Alright, well that is about it for today. That is all I have to show you. I'm pretty happy with how this is coming along. Getting everything integrated, getting all the software to talk to each other, and I'm able to send actual, real CubeSat data over the air using the radio. Pretty exciting. Next thing I'd like to do is get a proper range test in, see how far this can actually communicate, and I have some calculations I've been doing to see how far up in space could this actually reasonably transmit from. As always, thanks so much for watching.